tables today, and we'll work them from simple to more complex. All right, and this is first time I'm going to do it this way with you guys, so I'm going to try something a little different. Yeah, okay, that should be good. So I'm actually going to make it as simple as possible. So what we're going to do is we're going to be calculating equilibrium concentrations. Okay. From initial concentrations. Okay. Because at this point, really what you've done has been very clear. Like, here's the concentrations in equilibrium, find the equilibrium constant, right? So at this point, what we're going to do is you're going to be really given an equilibrium constant and asked to find the concentrations at equilibrium. And really, we're just going to give you the initial concentration. So what's going to happen is this is going to take some more steps. All right, so it takes more steps. Let's scratch that out. And an ice table. Okay, we'll use ice tables to help us out, to help us keep things in line. All right, and one thing that you will notice is that the reactants or the products, just to make these as simple as possible for us at this stage in the game, the reactants or the products will, reactants or the products, one will be the zero initially. Okay, one's going to be zero initially. So that means that we know which way the reaction is going to go to reach equilibrium then. If we know one is zero, it has to go that direction. We've got to make more of that stuff to get to equilibrium. Okay? Okay, so let's start with some examples. We're going to do 4 different examples. All right? And we'll put our quadratic formula to use at the end of today. Okay, in our last example. Yeah, so hopefully you got that program in your calculator for later. So it'll be great. All right, so the first examples, so we'll work from simplest to more complex today. All right, so our first example, our first couple are going to deal with solubility. All right, so how much is going to dissolve of a solid? Okay. So this first one, what we're going to look at is, let's say we have some silver chloride. And the K for this reaction is 1.77 times 10 minus 10. All right. And we want to find the concentration of silver ions and chlorine ions at equilibrium. All right, so let's write the reaction for this, for the dissolving of silver chloride. All right, so we've got silver chloride, and that's a solid, and it's going to dissolve into aqueous silver ions and aqueous chlorine ions. All right, that's what we're going to go into solution with. So if we were to write our KEQ or SP, call it whatever, what would be the equilibrium expression for this? What would be the K expression for this? Yeah, just concentration of Ag times concentration of Cl. right? Chloride ions. That's it. Right? Why are we worrying about silver chloride there? It's a solid, right? Okay. So let's set up an ice table here. So I stands for initial. C is change. And E is equilibrium. All right, we don't care about our silver chloride at all, right? Because it's a solid. It's not in our equilibrium expression. We don't care about the amounts of it at all. The stuff that we do care about and that we're interested in is our ions here, okay? So when we look at this, initially, right at the beginning, initially, we have 0 of each of these. And none of it has dissolved just initially, right away, okay? All right? We need to figure out what the change is going to be, right? For every one of these I put in, I get 1 silver ion, and I get 1 chlorine ion, right? I'll form the same amount of each one, okay? So that's going to be, we're going to call change plus x and plus x. So then in equilibrium, we should have some x value and some x value. All right, that's as simple as it gets. Okay, so once we got that, now we can just go ahead and plug this into our equilibrium expression. Okay, so we have K equal to concentration. I'm just going to write it again just for completeness, times concentration of chloride ions. So if we just plug our stuff in here, we plug our known values. They gave us the K in the problem, 1.77 times 10 to the minus 10. That's equal to x times some value x. Okay? And then we just solve for x, right? X squared is equal to 1.77 times 10 to the minus 10. So x is equal to square root of that. So I got 1.33 times 10 to the minus 5. And that's also equal to, hey, our concentration of silver ions and our concentration of chloride ions. Well, not multiply by each other, but equal. All equal, right? Our value of x is equal to silver and chloride ions. Solution. We can see silver chloride is not very soluble, is it? All right, it's not very soluble. Not much is going to go into solution, right? And that's the molarity. Okay. So that's it. All right. So not much is very soluble. And that makes sense because silver chloride is one of our precipitates. All right. So that's pretty simple, right? Let's dial it up a little bit.
Write down on the graph for number 3 how many grams of the KHP they used. You can't do it without that.
Well, we could have an idea. Should be somewhere like, right?
Okay. That's good.
So we'll be all right. We can ballpark it. All right, so the next example, we'll dial it up a little bit more. Very similar example, just like that one. Okay, except we're going to change it up just a hair. And we're going to take a look at, we want to find the equilibrium concentration of tin 2 plus and hydroxide ions when tin 2 hydroxide dissolves in solution. Okay, so I'll just give you the reaction here. So we've got tin hydroxide, solid, breaking up into It's ions, tin ions, and how many hydroxide ions? Oh, aqueous. All right, and the K for this is equal to 5.45 times 10 to the minus 27. Okay. All right, so just like we did before, initial change, equilibrium. We don't care about our solid. It's not in our equilibrium constant. 0 and 0. And what is our change going to be here? What do you guys think the change will be? Yeah, plus x and plus 2x. Right? So we ultimately, at equilibrium, will have x and 2x. Where did that come from? Where did the 2 come from? Coefficient, yeah, that's it. Just the coefficient, right? Because that's the mole ratio. For every one of these, we get out one of these, and we get 2 hydroxides, right? So the coefficient is what is helping us out there, right? We go with that? Okay. Yep. We'll get to that next. Yeah, I'll show you. That's what we're going to do next. When the initial's not 0, we'll talk. We'll show you what the deal is. Yep. I mean, we could do some stuff called like common ion effect, but you'll do that next year. Like next, you do AP and stuff, right? So we already have an additional amount of this, but 0 of this. So that we can see. You can still. We're still going to add to this side because we've got to form something here. If it's 0, we got to form some of it. So we'll still have to add, but we just won't be able to add as much. Yeah. Okay. So then we just plug this into our expression, right? Our K expression, our equilibrium constant expression. So we got concentration of tin times concentration of hydroxide. What do we got to make sure we do to hydroxide? Square it. All right, so when we plug it in, we get 5.4. Let's plug in all of our nodes. 5.45 minus 2 minus 27. We get x, and we get 2x squared. 2x squared. Make sure you have parentheses around that. It's a big difference, or it's still here on the board. There's a big difference between 2x squared and 2x squared. Okay. All right, so what do we ultimately end up getting over here? Right, we get 5.45 times 10 to the minus 27 is equal to, I'm going to break this down to a couple steps. Yeah. Uh-huh. Uh-huh. Wait, say that one more time. I didn't hear. Because the expression here is telling us the square. The amount of OH in solution is 2x. The concentration of OH would be 2x. And that's what's going to go here. And that value gets squared in our equilibrium expression. Okay, that's a good question. Yeah, that's a common question. All right, so yeah, we're plugging those in because that's our concentration of OH. And then we have to square that for our equilibrium expression. All right, when we plug these in, we get x, right, multiplied by, what is this value? 2x squared? Going to be? 4x squared, right? Here we go. And then what should it be now? 4x cubed. There we go. 4x cubed. just to reiterate, like, right, it's 2x times another 2x, right? So that's why it's 4x squared. That's where that's coming from. Just want to make sure we're good with that. Okay. All right, then you just solve for x, right? Kind of divide it by 4, 5.45. Divide by 4. 1.36 times 10 to the 27 is equal to x cubed. Then you gotta take the cube root of that guy. So math, cube root, second answer. So I got x equal to 0.11 times 10 to the minus 9. So x, so we got to go back up here, right? X is equal to the concentration of tin, 2 plus, but the concentration of hydroxide, right, is equal to 2x, right? So we got to multiply that by 2 to get 2.22 times 10 to the minus 9. So there's our answer. That's it. Right, we know that looking back at our ice table, right, we saw that we got x is going to be the equilibrium concentration for tin, and 2 times x will be the concentration for hydroxide. So that's just what I did down here, right? I found x, right? We found the x value, and we know that x is equal to 10, right? That one's good. Okay, so we're done with that. But hydroxide was 2 times x. So I took x and multiplied it by 2 to get that. Okay. All right, so those are the simplest ones. So now we're going to do ones where we got both products and reactants. So that means we're only going to have one that will be a 0, and the other guys will actually start with some initial concentrations here. Okay? We okay with that? We good with that? All right. So let's move on to our third example. Okay, these are more of the classic examples. The ones that we did above, we're not necessarily getting into it a bunch, but those are solubility problems, called KSP problems, solubility to product constants and stuff like that. But they work the same way as equilibrium constant. It's just an equilibrium constant. So this is more a classic example here. All right, so this is where you're still going to have, we have reactants and products, but one is initially 0. All right, one's going to be initially equal to 0. So here's the problem. So find all the concentrations and equilibrium for the following. Okay, so concentration of, and then we'll go initial concentration H2 is equal to initial concentration of I2, and those are all 0.2 molar. And the K is equal to 64. All right, so here's our reaction, H2 plus I2, going back and forth between 2HI. Okay, so we want to set up our ice table here. I, C, E. Okay. So what are my initial concentrations here? Right, we got 0.2, 0.2, and 0. It's not mentioned, so we're just assuming it's 0. All right, now the changes. Which way is the reaction going to go to get the equilibrium? Michael? To the right, right? We got to make more products to get there, right? All right. So because there's none here, so I'm not even going to do it. Like I could do it like this and give you an amount of this stuff initially, have you calculate Q, and then start going. I'm not going to do that to you. I'll just keep it simple. Okay. You're always going to have a reactant or a product that's going to be 0, and the reaction's going to move that direction in order to reach equilibrium. Okay? All right, so what should the change be? Should the change be here? So if this is going up, this is going to be positive. These have to be minuses. Right? If we're gaining one side, we got to be losing on the other. Because you gotta those need to come together to make HI. So what are we gonna put in there? Cornell?
Minus x and plus 2x.
Yep. There we go. So then we have 0.2 minus x, 0.2 minus x, and 2x. All right. Very good. All right, so let's plug this into our K. It's our equilibrium expression here. Just without any numbers in it and stuff. What's our equilibrium expression? What goes on the top, what goes on the bottom? Carly, can you tell me? HI squared, concentration of HI squared, okay. Okay, there we go. So now let's plug in our values here. So K is 64. We got 2x squared on the top. 0.200 minus x. And 0.200 minus x. Okay. Beautiful. All right, now, okay, this won't happen all the time, but what do we have here? Math people, what do we notice here about everything in our equation? Yeah, it's all perfect square. Yeah, you know, we can square root everything here, right? Because we got squared on the top. We got that's 0.200 minus x squared on the bottom. Okay, so we got perfect squares everywhere here. So we got perfect squares everywhere. We say a lot about people in the room like that, namely me. Nothing today. All right. Okay. Okay. See how it is. All right. So we got perfect squares. Okay. Perfect squares. So just take the square root. So just take the square root of both sides. So if we square root everything here, right, we get 8, 2x, and 0.200 minus x. And the math's just got a whole lot easier, right? It's nice. Okay, so all we gotta do is some algebra here. So if we do multiply each side by our denominator here, so we get 16 with a decimal, so 0.16, or 1.6 I mean, minus 8x is equal to 2x. Move that over, we get 10x equal to 1.6, and x is equal to 0.160. We're not done yet. We got to find the equilibrium concentrations, right? So in order to do that, right, we got to find EQ concentrations. So the concentration of H2, we got to go back up here to our table. We know what we're supposed to be doing right here, right? It's right here, right? H2 is 0.200 minus 0.160 to give us 0.040 molar. I2, right, 0.200 minus x, which is 0.16, equals 0.040 molar. And HI, that's 2 times 0.160, so 0.320 molar. So there we go. That's it. That's where we need to get to. That's what we want. Okay. Any questions? All right. All right, we'll do one more. Okay, last one. We're going to use quadratic formula here. Last one. So let's do this problem here. All right, same sort of deal. Find all equilibrium concentrations. All right, the initials, concentration of PCl5 is equal to 1 molar. The K for this reaction is going to be 16. And here's the reaction. So set up your ice table. If they don't tell you what it is, it's just 0. Okay? They don't give you an initial concentration, it's just 0. Okay, so how should I have my table filled in here? Olivia, what'd you put in here? Okay. Okay. And what are the changes? No. How do we know it's plus X is over there, minus X is over there? Yeah. Yeah, the direction is going to move to the left, right? Okay, it's going to go to the left. Because we can't have negative amounts of a physical substance. And then just either we have none or we have some. Right? There is no, you can't have less than 0. Okay? Your bank account can be less than 0, but in physical reality, okay, if you have $10, okay, then I give Anthony the $10, I have $0. Can't go negative. All right? How it works. Right? We can't have a negative concentration or a negative amount of the physical substance. Okay? That makes sense? That's going to help us out when we do our quadratic formula. All right, so here we go. Let's set it up. Let's see what we got. Right, because our K is going to be PCl5, concentration PCl5 over concentration PCl3 times concentration chlorine gas. So K is 16. We got 1 minus X over X times X. So we've got 1 minus X over X squared equal to 16. Okay, can we take the square root of this? No, unfortunately not. That means we're on our way to the quadratic formula. Okay, so we got to algebrate it out to get to a quadratic formula. What is the quadratic formula always equal to? 0. Great. So when you do that, I'm going to do it step by step here for you. So we multiply each side by X squared. Then I'm going to add X and subtract 1 to get them over to the other side. So I'll have 16 X squared plus X minus 1 equals 0. Quadratic formula. Let's do it. So what are my options for X? You got them on your calculator. Let's see if your program worked.
It's more like see if Miles' program works.
Didn't work. Uh-oh. Okay, so once if you got it, so you want to execute, so you just hit enter. Program function A, type in what A should be, right? A is 16. Nope. Uh-oh. Uh-oh. Got a problem with the formula. Rachel's is good?
I watched the video. I didn't do homework.
Yeah, Rachel. So what values did you come up with?
Point 221.
Okay, so you got either you got 0.221 or what?
Negative 0.283.
0.283. Those are the correct answers. Those are the correct answers. So you watch a YouTube video, right? These are the possible correct answers. Now, only one of these answers is viable for us. The positive one, right? We can't have negative concentrations. Can't have negative concentrations. So this one's no good. This one's good. Can't have negative concentrations. So X is 0.221. So X is equal to the concentration of PCl3, and it's also equal to the concentration of Cl chlorine gas, so that's 0.221. And then the concentration of PCl5 is equal to 1 minus 0.221, which is equal to 779. There we go. See, not so bad, right? Bad? Oh, I should have just let you, when I said we got to use Quadratic formula, I should have let you just get all the whining out now. When you feel better. Yes?
So you use the quadratic when you're doing a complex equation in the equation.
Correct. Yeah. If this was squared up here, we could square root it and we'd be good, but we can't square root everything. Okay. All right. So there you go. That's it. So that's it for today.